Okay, in the previous session, we have covered sources and detectors and general bridge balance condition for any AC bridge. So in today's session, let us see measurement of inductance and measurement of capacitance. So in measurement of inductance, we have Maxwell's inductance bridge, Maxwell's inductance capacitance bridge, Hayes bridge, and Anderson's bridge. For measurement of capacitance, we have shearing bridge and de Sauty's bridge. These are the names given to the bridges, out of which in your 18 scheme syllabus, Maxwell's inductance bridge has been removed. You are going to study only Maxwell's inductance capacitance bridge, Hayes bridge, Anderson's bridge, and for capacitance, shearing bridge and de Sauty's bridge. The reason why I am mentioning all the bridges is totally 4 bridges are there, bridge circuits are there to measure inductance, out of which only 3 are there pertaining to your 18 scheme syllabus. So please don't waste your time studying about Maxwell's inductance bridge. In some of the textbooks, syllabus may not be updated and you might find Maxwell's inductance bridge also. Okay, so let us start with Maxwell's inductance capacitance bridge. So here, this is the arrangement, this circuit diagram what you are seeing is the arrangement of Maxwell's inductance capacitance bridge. Here, L1 is the unknown inductance, R1 is the series resistance along with this unknown inductance, and we have R2, R3, R4 and C4 connected in the fashion that is shown over here. R4 and C4 are variable elements. In order to achieve the bridge balance, we need variable elements. So R4 is variable resistor, C4 is variable capacitor. So whenever we need to understand any bridge for measuring any passive element like inductance or capacitance, first we'll have to draw the circuit diagram, analyze with the phasor diagram, and then we'll have to mathematically derive the expression for unknown inductance. So this is the circuit diagram. We are having a detector in between B and D, and we are having the source connected between A and C, nodes A and C, and the unknown arm is between AB, where we have R1 and L1, which is the unknown inductance and this corresponding series resistance. Our intention is to find the values of R1 and L1. R2, R3, R4 will be known to us. C4 also will be known to us. So first let us see the derivation part. In order to find the expression for unknown inductance, we start with general bridge balance condition, which says product of opposite impedances magnitude are equal. Magnitude of the product of the opposite impedances are equal. So the impedance of arm AB is Z1, impedance of the arm CD is Z4, impedance of arm BC is Z3, and impedance of arm AD is Z2. So we already have seen the general bridge balance condition. So we are implementing the same here. Z1, Z4 equal to Z2 into Z3. Now we'll have to substitute for Z1, Z4, Z2 and Z3. So coming to Z1, Z1 is a combination of series resistance and inductance. So if we try to write the expression for impedance here, it will be in the form of R plus JXL. So it is R1 plus J omega into L1. XL is nothing but omega L1 because it is 2 pi FL. So 2 pi F is nothing but omega. So it will be R1 plus J omega L1. Since it is arm 1, we are using the subscript 1. Then coming to Z4. So in the arm CD, we have a parallel combination of R4 and C4. So coming to the reactance offered by the capacitor, it is nothing but minus JXC4. So since R4 and C4 are connected in parallel, the equivalent impedance will be R4 into minus JXC4 divided by R4 minus JXC4. Similar to your two resistances in parallel where you had R1 R2 by R1 plus R2. Here we have one resistance and one reactance. So it is R4 into minus JXC4 by R4 minus JXC4. Coming on to the RHS, we have Z2. Arm 2, we just have a resistor, so we write it as R2. In arm 3, that is BC, we have resistance R3, so we write it as R3. So we have substituted for impedances in LHS as well as RHS. Now we'll have to mathematically simplify them. So we have R1 plus j omega L1 multiplied by R4 divided by j omega C4 divided by R4 plus 1 over j omega C4, as you can see here, is equal to R2 into R3. If you take LCM and simplify, we have R1 plus j omega L1 into R4 divided by 1 plus j omega R4 C4. This is equal to R2 R3. Now let us transfer this denominator to the RHS. So we have R1 plus j omega L1 into R4 is equal to R2 R3 multiplied by 1 plus j omega R4 C4. Then we'll simplify this expression. So we have R1 into R4 j omega L1 into R4 on LHS, on RHS R2 R3 plus R2 R3 into j omega R4 C4. So R1 R4 plus j omega L1 R4 is equal to R2 R3 plus j omega R2 R3 R4 C4. Now what we have to do here is equate the real and imaginary terms on both the sides. So on LHS side, the real term is R1 R4 and j omega L1 R4, which is coefficient of j, refers to the imaginary term. Similarly on RHS, R2 R3 is real term, coefficient of j is the imaginary term. So if we equate R1 R4 on LHS will be equal to R2 R3 on the RHS. So from this we will get the expression for R1, which is R2 R3 divided by R4, call it as expression 1. Now try to equate the coefficient of j on both the sides. So on LHS we have omega L1 R4, on RHS you have omega R2 R3 R4 C4. So omega and R4 gets cancelled out, you will be left out with L1 equal to R2 R3 and C4. So we have found the expression for the unknown resistance and inductance connected in arm 1. Then whenever you deal with a coil, always we are interested in knowing its efficiency, that is nothing but quality factor. So quality factor is given by XL by R in general. Pertaining to this case, it is XL1 by R1. So our omega L1 by R1, where we substitute the expressions for L1 as well as R1 that we have got over here. So omega into, in place of L1 we write R2 R3 C4, and in place of R1 we write R2 R3 divided by R4. If we simplify, we get omega R4 C4. So this is the expression for quality factor of a coil. Then we'll have to discuss about merits and demerits of Maxwell's bridge. So this is our Maxwell's inductance capacitance bridge. Unknown inductance will be measured here. So initially whenever you are connecting this unknown arm in this particular bridge will be under imbalance condition. Current will be flowing through the detector. So we'll be varying R4 and C4 to achieve the bridge balance. So at one point of time, bridge balance will be achieved. So then we'll be deriving for the unknown inductance and series resistance that we have done right now. Then coming to the merits and demerits of this bridge, the two balance equations 1 and 2 are independent with R4 and C4 as variable elements. So if you just refer to equation 1, we have only one variable element R4, we don't have C4. Similarly, when it comes to inductor, we have C4, we don't have R4. That means in order to achieve the balance in the bridge to find out the unknown elements, varying one element will not disturb the other element. If you vary R4, only R1 will get affected. If you vary C4, only L1 will get affected. So they are not interdependent. They are independent of each other. That is one advantage. Second advantage is the two balance equations are independent of frequency. There is no frequency element in both the terms. We don't have omega, it has got cancelled out. So omega, that is 2 pi f, is not present in both of them. So it will be very easy to handle the bridge. Then the third advantage is bridge is used to measure wide range of inductance at power as well as audio frequencies. So with wide range of frequency, this bridge can be used. Coming to the demerits, this bridge can only be used for the measurement of inductance of the coil having quality factor in the range 1 to 10. So quality factor, I told you, is the measure of efficiency of a coil, and its range between 1 to 10 only can be used for measuring the unknown inductance in this particular case. So if we use Maxwell's inductance capacitance bridge, it will work very fine or very good only for the range of the quality factor 1 to 10. That's the disadvantage. And the next one is this bridge requires variable standard capacitor, which is expensive. The C4, what you can see here, is very expensive. That is the another disadvantage. Next, we'll have to go for phasor diagram of this Maxwell's inductance capacitance bridge. So before that, let me cover up with one more bridge circuit, and together for both the bridges, I'll explain how to draw this phasor diagram. Next, we have Hayes bridge. This is another bridge circuit used for the measurement of unknown inductance. So let us see the circuit. We have R1 L1 connected in arm AB, which is the unknown element, that is unknown inductance in series with the resistance. We have known resistances R2, R3, R4 connected in other arms, and we have C4 also connected in arm CD. So here this bridge is basically modification of Maxwell's bridge. In order to overcome the demerit that we have seen in Maxwell's bridge, this bridge is brought into existence. So you can see this bridge is suitable for measurement of coils having quality factor greater than 10. If we use Maxwell's inductance capacitance bridge, the range is only from 1 to 10. Beyond 10, if we want to measure the inductance, we have to use Hayes bridge, that is this particular arrangement. So the arrangement goes like this. In arm AB, you have R1, L1 unknown elements. Arm BC, you are having R3, which is known to us. Arm AD, we have R2, which is again known to us. And arm CD, we have series combination of R4 and C4. The values are known to us. Then we have marked the currents I1, I2, and we have marked the potential across each and every arm. That we'll discuss in detail when I am explaining the phasor diagram. Now, as usual, let us go with the derivation for finding the unknown inductance. So, as usual, we start with bridge balance condition. We have Z1, Z4 equal to Z2 into Z3. So, coming to Z1, we have a series combination of R1 and L1. So, the impedance will be R1 plus j omega L1. And here in arm 4, we have series combination of resistor and capacitor. So the impedance will be R4 minus jXC4. And then on the right hand side, we have Z2. Z2 is nothing but R2. We just have only resistor here. And in arm 3 also, we just have only resistor. So R2 and R3. Then we are going to simplify this. So we have R1 R4 minus j R1 into XC4. Then j omega L1 R4. Then plus omega L1 XC4, because j square is minus 1. So it becomes plus omega L1 XC4. This is equal to R2 into R3. Again, in the next step, R1 R4 minus j R1 divided by, instead of XC4, I'll be writing 1 over omega C4 plus j omega L1 R4. Here we have omega L1 divided by omega C4. That is, XC4 is written as 1 over omega C4. Omega gets cancelled out. This is equal to R2, R3. As usual, we are going to equate the real and imaginary terms on both the sides. Then the real terms, if you equate, you have R1, R4 plus L1 divided by C4 is equal to R2, R3. Please check it here. On the LHS, we have R1, R4, and then we have L1 divided by C4. On the RHS, you have R2, R3. So R1, R4 plus L1 by C4 is equal to R2 into R3. And coming to the imaginary terms, let us see the equation. We have minus j R1 by omega C4 plus j omega L1 R4. So the coefficient of j refers to the imaginary terms. So if we equate the same, we have omega L1 R4 minus R1 by omega C4 is equal to 0, because on RHS we don't have any imaginary term. So this is equal to 0. So we have omega L1 R4 is equal to R1 divided by omega C4. So L1 will be R1 divided by omega square R4 C4. This is equation number 2. So we have found L1 over here. Now we'll have to use this expression for L1 in equation 1 in order to get R1, because L1 is also unknown here. R1 is also unknown over here in equation 1. So we have found L1, we'll be using it here to get R1. So substituting 2 in 1, we have R1 R4 plus, in place of L1, R1 divided by omega square R4 C4 multiplied by C4 that is already there is equal to R2 R3. Multiply this, take LCM. After simplification, we have R1 equal to omega square R2 R3 R4 C4 square divided by 1 plus omega square R4 square C4 square. So this is the expression for unknown series resistance, and unknown inductance is given by R1 by omega square R4 C4. Then you please observe that even over here in the second equation, in the expression for L1 we have R1, so we have to substitute for R1 whatever we have got here, so that we get the expression for L1 independent of R1. So I have in place of R1 omega square R2 R3 R4 C4 square by 1 plus omega square R4 square C4 square divided by the denominator omega square R4 C4. Terms get cancelled. You will be left out with R2 R3 C4 divided by 1 plus omega square R4 square C4 square. So now the expression for L1 does not contain R1 inside. At the same time, the expression for R1 also does not contain L1 inside. So both the unknowns are found. This is how you generally solve any simultaneous equation. Two variables, two equations. So equation 3 gives the unknown resistance, and this expression for L1 gives us the unknown inductance. Now, as usual, we find the expression for quality factor given by omega L1 by R1. So in place of L1, substitute R2 R3 C4 by 1 plus omega square C4 square R4 square, and in place of R1, substitute this expression. Simplify, we get quality factor Q is equal to 1 over omega R4 C4. So if you want to express this L1 in terms of Q, that also can be done. So you have the expression for L1 over here, which is R2 R3 C4 by 1 plus. In place of 1 by omega R4 C4, you can call it as Q. So it becomes 1 over Q the whole square. So if you want, you can measure this inductance in terms of quality factor also. But of course, if we derive the expression until this 1 over omega R4 C4, that is good enough. Again, coming to the disadvantage, for higher quality factor, it doesn't demand higher value of R4. But the trouble here is bridge is not suitable for coil having quality factor less than 1. It is suitable for value of quality factor greater than 10, but it is not suitable for coil having quality factor less than 1. So this is it with Hayes bridge. So we have seen Maxwell's inductance capacitance bridge to measure the unknown inductance, and we have also seen Hayes bridge for the measurement of unknown inductance. Now we'll have to analyze this phasor diagram. Step by step we'll have to see how to draw the phasor diagram. So let me continue with the phasor diagram.